We're going to be talking about Escher. I do recommend these two books. Either one of those are very well worth having. Beautiful pictures in them. This is actually a second broadcast about Escher. His art is very mathematical, and he had insights which were truly genius. He was a genius when it came to being able to see the geometry in shapes and the way they fitted together and filled space. He was, as a young man, he went to Alhambra, the palace in Granada, which was set up by the Moors when they ruled Spain. They were a very cultured society, far ahead of the rest of people in Europe. And they explored quite a lot of mathematics. And amongst those things were these patterns, these 17 patterns that fill space. And the pattern you see above is one of the patterns from Alhambra. Now, here you have a notebook in a note from Escher, where he explains a little bit about how shapes fit together. And what you see there is a lot of triangles, and you might look and you might be able to see a hexagon in there made up of 6 triangles. But why Escher made this note for himself was he was noting 3 geometrical transformations, we call them. One where points just move along a line, and the arrow that goes from A to B shows you that that whole pattern can shift along horizontally. The mathematical word is translate. And the whole pattern will move to look exactly as it is now, but move to the right. You can make the pattern stay the same by doing a reflection where P goes to Q. And that line that's dotted and dashed, that was a note to say that there is a reflection in that horizontal line through A, B, and C, where P is reflected in that mirror and goes to Q. And then the third note he makes there is about rotations, where the whole plane can rotate so that the line that goes through C, the sort of thick line that goes through C, rotates anti-clockwise. Oh, that looked clockwise, I think. I'm not sure. Anti-clockwise, anyway, through 60 degrees. And of course, it rotates the other way.
It's anti-clockwise.
Yes, and it rotates the other way.
So it can go either way.
The gesture I made with my hand.
Oh, your hand. Oh, yeah.
Was doing the other thing.
Yes, yeah. Just use both and say, well, it's going to go one way or the other.
No, I was doing it.
I understand.
I was doing it.
Hence,
well,
use both, and then you know one of them's right.
Never mind.
One thing I love about Escher is that he was, we can go back to that one just for a moment, Tony. He did not consider himself to be a mathematician. He thought, well, I'm not a mathematician. And he considers himself to be less than the mathematicians that he worked with. And yet, well, this is a basic thing that we learn in higher primary, lower secondary, these transformations and rotations and mirror symmetries, but he used these concepts, as you will see shortly, with some very, very complex mathematical ideas. So he had the mind of a mathematician, if not the formal training of one.
So what he did was he explored 17 different groups of transformations. And by that I mean, as we just talked about them, reflections and glide reflections, rotations and translations. And that will copy the plane nature again to look just the same, but to be changed by one of those transformations. And copies of a shape fill the plane. He was very interested in filling the plane with repetitions of the same shape. So here you see black and white birds filling the plane. And here this plane was actually wrapped around a column. So it was like on the surface of a cylinder. But here we're just going to see some glimpse of these 17 different groups. We're not going to go into the maths in detail. Now here's another note made by him here he has done a design of these little men with the pointed caps, and the men are sort of whitish and dark grey and light grey. You can see them, and that's, again, if you look, you can see triangles there. That's based on a tessellation, or putting together of triangles. That was quite early on, 1938. Now this is beautiful. It's called Sun and Moon. Now, when you look at it, you may see the grey birds with the sun behind them. And then if you look again, you may see the white, orange, red birds with the night sky behind them.
I think you need to leave this on for a little bit longer, Toni, because it took me a while to spot it. I could see, because the sun is red and yellow, and that had me a bit transfixed. You can see the rays of the suns coming out red and yellow. The moon and the not just the moon, it's the night sky is in the grey. So if you look at the colouring of the grey birds, that's where you'll see the moon in the centre.
To see the night sky, you've got to look at the white birds, and then the night sky is behind them. To see the day sky, you've got to look at the grey birds, and the daylight is behind them.
See, that's why I see it the other way around. I actually have to look. Everyone's got their own way of looking at things. So Tony's said one way, I've said another, but I had to look at the grey birds, into the detail of the grey birds, in order to see the night sky. So
well,
whichever works for you, but it's there. So have it.
But the point is, the grey birds are supposed to be flying in the daytime, and you're not supposed to look at the with the sun behind them, and the white birds are supposed to be flying at night with the night sky behind them. But
okay, right, I see your point.
but isn't that interesting? Different people see different things. Yeah. Absolutely. Anyway, this was a woodcut, if you're interested in the craft behind it, which means that he carved it with blocks and wooden blocks, and then they were dipped in the colours, and he's using quite a number of different colours there, and printed. It must have been done so precisely for them to fit together as they do, because there are different shaped birds there, and they're all fitting beautifully together. But it's a tessellation. Now, here is something you might like to try for yourselves. You can cut out any triangle out of card. Any angles will do. And then, if you're careful, you can keep drawing around the edge of your triangle, moving it along, drawing around it again, and matching the edges, and make what we call a tessellation. Now, tessellation is where the same shape fits together again and again and covers the flat space, the plane. And you can do that with any triangle.
So typical tessellation would be tiles on a floor or tiles on a wall. They tessellate, they completely cover the wall, completely cover the floor. And tessellation is an art in of itself, and Escher just took it to another level, didn't he?
Mathematically speaking, there's a difference between tessellation and tiling, but Caroline's quite right. Then you see...
But aren't square tiles, don't square tiles tessellate?
They do, of course, yes.
So I should have specified square tiles.
No, no, you shouldn't, Caroline. No. Mathematically, tessellation and tiling are slightly different. And the difference is that tessellation is according to it's according to a pattern which repeats itself. Now, what you described as a tiling is a tessellation, but not all tiling is a tessellation.
Right, fair enough. There's no problem there. I was imagining plain white tiles, as it were, just covering a wall, and they're all the same shape. They're all squares. So yes, so yes. Be careful, everybody.
No, you don't have to know. It's not. Yeah.
I just learned something new, which is great. I've learned another new thing today.
Yeah. Okay, so quadrilaterals also tessellate. So you can do the same thing with a quadrilateral and any quadrilateral, and you can fit copies of it, and you can use it as a cardboard quadrilateral as a template. And then this is just the sort of thing, but much, much, much more detailed, that Escher did. By taking your basic shape, let's look at the triangle now, you can take a little bite out of it, okay, and you can make you can add that same shape to the edge on the other side. You take the bite out and you put it back on the other side, and then you have changed your triangle now into a 5-sided shape, but your bite doesn't need to have straight edges. Think of doing a jigsaw puzzle, you know, the standard jigsaw puzzle. That's got a rounded piece, or lots of rounded pieces that stick out, and other rounded pieces into which they fit.
And am I right in saying you can do this on the other 2 edges as well?
Any edges, and you
any of the edges. Yes, this boggles my mind. And I even had difficulty, Toni. I knew that squares tessellate, that triangles tessellate, although I was kind of a bit fixated on regular triangles where all the equilateral, where all the edges are the same length, all the angles are the same. I'm like, well, that's obvious, they tessellate. But Toni said, no, any shape triangle. I'm like, really? And then any shape quadrilateral. So where was me after that? I was off cutting out all these bits and different shapes and making them all the same, of course. Once you've cut one out, they've all got to be exactly the same shape. And it's just a matter of how they fit together. It's not whether they fit together, they do. And this then is the next bit that we're going to cover, but it's like, and then you cut the bits out of it and you add the bits in, and as long as they're the same shape, they all tessellate. Blows my mind. And
but
then
you see, Caroline, my challenge to people is to look at this slide and take a basic shape like a triangle or a quadrilateral and draw around it. You only need to cut one out of card. Take a piece of paper, keep drawing around that same, use it as a template, keep drawing around it, make your grid, and then start being creative. Can you make a bird? Can you make the wings stick out? And then can you make it so that it will then repeat itself, and the bits that stick out will fit into something that's a little bit of a hollow somewhere else, and you make your design. It'll take quite a lot of experimentation, but if you like this sort of artwork, then there's a challenge for you, and I'm sure you'll come to it, respect and admire Escher even more for the wonderful designs that he made, because it's not easy to do it.
And yeah, and the reason I was going back a step, Toni, is because I found it hard to believe. I mean, I took your word for it, but I had to do it for myself before I actually saw it for myself. Yeah.
Yes, Caroline, but the next thing, which I don't want to go into here because we've got lots more pictures to talk about and show, but the next thing with this is you tried it by doing it practically, but then somebody else, or maybe you too, would like to try it by proving it geometrically. Why does it happen? I'm going to leave it there because I want to move on. And here we have another design. Now here, this is actually a design which has got 6 edges, and it's sort of got kinks pushed into it at the side, like a waist from X to Y, okay? And there's the details, which I'm not going to read, and you can read for yourself, which show you how to make that shape, starting with the easy shape, the parallelogram, KLMN, okay? And if you make that shape, you can tessellate with it. So to tessellate copies of this irregular hexagon, you'll need to rotate the shapes about the midpoints of the edges. And all I'm saying is try it. I'm not asking that you can see it now at this minute, but it's there for you. You'll be able to have access to this recording of our show today, and we'll also post the PDF, which will give you all the slides with these things on. So if you're interested, you can try it for yourselves. Now here you see some more tilings of hexagons. And so we're using color here. They're all hexagons, but there's 3 patterns and each pattern has a different shaped hexagon. And we're asking here, what's the smallest shape that repeats itself just by translations to fill the plane? Not by rotations, not by reflections, but just pushing the thing along and moving it to the next thing, the copy of itself. Yeah. Now, the one on the left, the reason we've got 4 colors there is that if you focus on, start at the top left-hand corner, if you like, and you focus on the green, yellow, pink, and mauve copies of that shape, it's all the same shape, but if you focus on those 4 copies, then you see you can move one green one along to the next one, and then that will take with it the yellow one and the pink one and the mauve one. And you can do that by moving it down as well. So when you count round that shape, which is made up of 4 hexagons, you'll see it's got 14 edges. And you can use that to tessellate or tile the plane. And here the same thing applies. And here we've got, oh, by the way, the reason it's called periodic means that you can do it over and over and over again. We've only shown you a few copies here, but you could go on forever out and as far as you like and use it as wallpaper to cover your whole wall. I'm not sure I'd want to see that on the wall every day, but there you are. These are called wallpaper patterns, by the way. The one in the middle has only got 2, so actually, if you take the pair, the green and mauve pair, you can move them down or you can move them across, and you see it keeps repeating itself. And the one on the right has got 3 colors, and if you look at the shape made up of 3 colors there are 5 copies of it, and it does again the tiling.
It's like a stamp.
Yes.
You can see where you could, the stamp that repeats itself, locate, find the basic form, and that's your stamp.
And yes, and you've seen these sorts of patterns in many places. They're commonly called wallpaper patterns by mathematicians, but you've seen them on fabrics, on curtains, on dress materials, as well as wallpaper. You've seen them, as Caroline mentioned, as tiles on a patio, on the floor, on bathroom walls. Many, many places you'll see these repeating patterns. Okay, so you'll see amongst our pictures we're showing, Escher's pictures we're showing, you'll see more of these tessellations. But he explored other mathematical ideas. He explored the idea of spirals here, and spirals on a flat plane like the red and brown fishes there, but also spirals that went round and round around the edge of a donut shape. You can't see the whole shape. I like the one on the right. That one, the spirals go round and twist round in a ring, but as you go round, the ring gets bigger. That's fascinating, isn't it?
It's as I said, he had the mind of a mathematician, if not the training of one. It absolutely mind-boggling.
But it's, you know, they're beautiful to look at too.
And now, this one is one of my favorites, because these are all shapes that I work with balloons. So I love this one.
Now these are called the platonic solids. Okay, and there you see the 5 shapes that are sketched down the middle, they were discussed by the Greeks, and he was Plato's name has been attached to them. And as Caroline does a lovely entertainment where she makes these out of balloons. But Escher has played with these shapes, and he's made this. This is from his notebook on the left there, where he's written in the names of these shapes, so you can read them there. And and here on the right, you've got this cube octahedron, and these funny creatures inside it. And their tails wrapped around the edges of it. Isn't it amazing?
Well, that's not a cube octahedron, Toni, but
I think it is.
Okay,
it is.
Right. We'll have a discussion later, not right now.
A cube octahedron has. You can see the squares there.
What I see is two octahedra inside each other. It's a two octahedron rather than a cube octahedron.
That's exactly what you see, yes. And if you see it's up on the left-hand side, just under the bubbly mass, it's labelled there, Caroline. And that's the solid one, and the right-hand one where the beasties are is in just a skeleton.
Oh, it's a three octahedra then. There's three of them.
Now we're going on to his exploration of 2 and 3 dimensions. And this is a very famous one where you see probably they're his hands sketching his arm, which is now dissolved into the paper. So you've got the flat piece of paper with the hands coming out. Of course, it's all flat.
And yet the flat piece of paper doesn't even look flat. The flat piece of paper looks as though it's had to stick the piece of paper down with tacks because it's coming away from the desk. It's absolutely incredible.
Now look at these. These are amazing. So in this one on the left, which is called Encounter, the encounters are between sort of little men and little black beastie things with big noses, okay? And they've come out of the picture behind, and
which is flat. It's flat at the back.
And
like
they've come out and look pretty solid in the front. I mean, that's just amazing. He called it Encounter. And the one on the right is even more amazing. And they show you how he was exploring mathematics. So he's got these reptiles, lizards or crocodiles. They don't look fierce like crocodiles. Anyway, they're flat on the page of the book. And then they're crawling out of the page, crawling up over the book. And then there's a ramp, which is a trapezium shape, onto the solid shape, which is a dodecahedron, and over into that sort of cup, and then down and slithering down back into the flat page again. Isn't that?
I just noticed it's like a wingless dragon, because one of them's actually blowing smoke or steam out of its nose right at the top there. I don't even notice
so he is. So he is.
But they're fantasy creatures.
and he's the cactus is sort of a ball there, a sphere, not quite, but more or less. He's also put two cylinders in the front with the bottle and the glass there. I mean,
it's just absolutely the detail and what the thought that's gone into that is just
incredible. Well, he's obviously exploring some shapes and mathematical, and for me, the shapes are mathematical ideas. Okay, so that's exploring 2 and 3 dimensions. Now this gets more and more, mind-blowing. Here we have got impossible worlds, he called them. And the thing about this is, if you look at a little piece of it, it looks perfectly okay. Nothing impossible about, if you just look round the corner of one of the corners of the crate or one of the corners of the tri-bar, it looks all right. But when you look at the whole thing, you realize it's impossible. And he played with that idea. And Roger Penrose is a mathematician, he's a professor at Oxford. Well, he's retired now, he's sort of about my age. And Yes, he and Escher did quite a lot of work on this sort of thing, on tiling too. Roger did a lot of research on tiling. Now we've got some of Escher's pictures, Impossible Worlds. And this one is called Ascending and Descending.
This is one of the most famous ones that I've seen this repeatedly, and it's absolutely bonkers.
If you look at the top, that sort of the staircase that goes round on the roof there, near the roof, around a quadrangle. I mean, when you look at it, you can't be sure. I mean, some of the people appear to be going down, other people appear to be going up, but it's a continuous staircase. So it's just mind-blowing.
It's impossible, but it's so mesmerizing looking at it. You know, well, it's going on forever, and you just don't stop. And then you go the other way, and they're all going down, and they're all going up. Wait a minute, they're going next to each other, and it just never ends. It's amazing.
Well, actually, the crate was a clue, wasn't it? He obviously used the idea of a crate, which you've just seen, in helping him to make that design, and impossible.
Yes, I still don't know how he's done it.
Nor do I. Now this one, again, you find actually it's even harder to see the contradictions here. Here, this is called Belvedere, with the lady with a long train there and a funny hat with horns, and at the bottom.
This one, he's actually, it is deceptive, because the top layer, as far as I can see, is just normal. It's got 3 domes, and each dome has four columns, whatever.
I think once you begin to look at the columns, you begin to wonder. But
not on the top layer, though.
Okay.
On the top layer, I don't see, apart from one column at the back is a little bit not wide enough, perhaps, but no, the top column, the top layer, I think is okay. I haven't seen anything. But that's deceptive, because then you look at the middle layer where the man's standing, looking away towards the mountains, and where the ladder begins. Look at that layer. Look at the columns and the arches on that one, and tell me how that can happen.
It can't. It's impossible. Now this one is just again, it's just intriguing. You have 2 versions of the woman looking out the window and the man on the staircase looking up at her, but in the picture they appear to be drawn looking at different angles. And if you look at the top and bottom, well, Caroline was telling me this afternoon that she looks at the middle, but I tend to look at the top half and the bottom half, and it's like a spot the difference game. But they're all merged into each other in the middle, which makes this sort of impossible pattern in the middle.
They're a copy of each other. The top and the bottom are a copy of each other. Let's say they're looking at the same thing from 2 different perspectives. But the fact that they're all in the same picture, I suppose in this day and age, we have those rotational, you can see 360 degrees, but 360 degrees isn't going to give you 2 copies of the same thing. It's just going to let you see all the way around it. So what I saw was that in the center, the little patio area in the center, you have the same building coming out upside down, whereas one building's coming up the right way up, the other one's coming upside down. It just, whichever way you look at it, you can see different things and different perspectives, and
it's somehow a bit like when you go into these halls of mirrors with distorting mirrors, and it makes you look really odd. Everything around looks odd.
You can just go back to that other one again. There's a third thing happening, and that is on the right, the column on the right. It's been connected to the picture on the bottom with arches, and you can see the identical one on top is connecting to it with arches. So it's been connected at the bottom and at the top, and you can't even see it. It's happening, but you can't even see that third column, that third building. Or second building, whatever it is. There's so many questions around it.
I mean, I think find that quite disturbing to have on the wall. But there are some of the more peaceful ones, like the sun and the moon, are well. This is intriguing as well. But I wouldn't. I'm not sure I'd hang it on my wall. Maybe. Now this one is called Relativity, and here again, you've got an impossible staircase. Okay, but now you've got people going up under and coming down underneath, and stairs on the top as well. Oh my goodness.
I feel this inspired Hogwarts. I think this is where Hogwarts came from. And
Magic.
You've got people walking horizontally. You've got people. There's one person sitting on the wall facing down, and I don't actually see anyone upside down, but there's definitely people sitting horizontally. And what I do is I imagine what on earth was going on in this man's head. How on earth?
No, he's been deliberately perverse. He's actually seeing how crazy he can make it, because he's making an impossible world.
Yeah, no, it's amazing.
I mean, in this world, you've got floors which people are walking on, which are actually walls, and walls which are floors. Oh, it's crazy.
And they are actually walls as well as floors. Yeah, it's beautiful.
This one is he calls waterfall. And here the water is flowing continuously, but is it flowing up? It appears to be on that zigzag, and then coming down on the waterfall, which is going straight down. I mean, it's just crazy, isn't it? It's just wonderful how he can actually make it look like that. Okay, so escaping from the impossible world, we come into the world of knots. Now, believe it or not,
did you do that on purpose?
Yes, knots. The theory of knots is a mathematical area of research. It's called
knot theory. Strangely, yes, and it's wonderful. It's wonderful playing with people that study knots. There's a gentleman from Ireland.
Yeah, my husband now, he's retired. He used to have his own office, but he now has an office that he shares with somebody called Ray, who's a knot theorist. And so in my husband's office, he's got pictures of knots on the wall. Okay, so Escher explored knots too, and he did some knots in his artwork. There's knots. Okay. Now this one we're going to spend a little time on this, because isn't it amazing?
Can I just fill in the bit that I missed when I first looked at it? This is one long picture that starts on the top left, and then it continues on. The one below it is the next one, the one below it's the next one, the one below it's the next one, and then the next four other four as it continues. But this is actually pictures of one very 7 meter long picture, and it's been divided into 8 segments.
Well, here. Yeah, exactly. So the depth of it is about that deep between my two hands. Okay,
yeah.
It's just less than 20 centimeters, but it's 7 meters long. That's huge. And here you'll see, you sort of read it like a book, really. So as you read along the top piece where you've got the word metamorphose in grey, it becomes pretty much a regular checker pattern, which then becomes a little bit wobbly and into a beehive pattern. And you actually see some small bees there, but they're pretty vague, and some more later on. And then it goes back again, or maybe that's a bit of the pattern repeated, actually.
Well, I don't know, because it does go into the beehive. It goes into hexagonal stars, five pentagonal, which means you've got some, and then it goes back to squares, and then it goes, after that it goes into the hexagons.
Yes. So the thing about it is, yes, you're right, Caroline. So if you're looking at this, you need to look at each time go down one to see the next one.
Left, and then go down.
And then you go down the left hand foot 4, and then you start at the top again with the fish, the hats and the fish, and go down the right-hand four.
Yeah.
So going across the second strip on the left, you see the checkerboard again, and then that goes into some...
Like, they're almost snowflakes, aren't they? But they're snowflakes with bees on them. So
they've got little frogs there. You can see frogs. Yes.
Oh, yes, before the hexagons, between the squares. Yeah, he does a frog and then turns into kind of lizard kind of things, and then frogs, and then turtles, and then hexagons.
Okay. And then the hexagons make a beehive again, and now we've got bigger, more clearer bees. Right, and then they're flying, and the bees become birds, and then they merge with the fishes who are swimming the other way. You can still see the black birds, though.
Yeah, the birds keep going, don't they, for quite long, and then they almost become whales a bit later, maybe not. And then, the white becomes the hats. The white part of it become hats.
Yes, the birds, which were black, as you say, I'm not sure whether they're whales, but they certainly look more like swimming things than they do. Yes. So then you've got the hats, and then you go to the top again, and the hats are mixed up with more fish. And as you keep going right,
the fish suddenly become the gaps between the horses.
And then you see horses.
Where did they come from? And then they almost look like goats. Further on, the horses turn into goats. Yes. And then the birds appear again. In fact, initially when you see the goats, that kind of looks like they look like phoenixes. They kind of look like firebirds in between the what looks to me like goats.
And then the birds turn into triangles.
And then it's like almost origami birds in that next section.
But birds are flying out. Then you've got a sort of, in this second one down on the right, you've got sort of a suggestion of a triangular tessellation behind. But there's some birds on the left. There's sort of different shaped birds, and then more birds on the right.
I'm going to call them origami birds. I think they're just like origami birds to me. But then they turn into real birds, don't they? And then you've got the black birds turning into white, or merging with white. They look more like flowers than birds then at that point.
And then it begins to get three-dimensional, because you then get blocks, which then become a city.
Which is completely random, because that is not any kind of tessellation, is it? And yet it's beautiful. It's extraordinary. You've got the fields at the bottom, which end up being... It's actually a cube, Tony. Look at that. The chessboard is actually a cube shape.
Well, what is so clever is there's a sort of bridge from the city to something which looks like a tower, but then it's actually a knight.
Yes.
It's not a knight, it's a castle.
A castle, yeah. Or a queen. It could be a queen. It look more like a queen.
Well, it could be actually. Anyway, it's on the chessboard.
It's the tower, but the queen does look like a tower. So
yes, and then you've got it as three-dimensional, but then it flattens out. Well, you just got a checkerboard, and then you're at the bottom, and then it fades away into the grey, and the word metamorphose again.
Yeah, it just ends the way it began. It's absolutely incredible.
Now, this idea of metamorphosis, which means change your form, your shape, you see it's there. That's what he's exploring, how one shape gradually changes into another.
This is something that's is a common thing these days with CGI. Morphing happens all the time with cartoons these days, and even with real life characters, because using CGI, actors can be transformed into something completely different using computer graphics. But it's the same principle. They're morphing, and it's exactly the same principle but Escher had to do it with pen and ruler and paper, and look at what he did without any computers at all.
But if you get somebody in an animation, a lot of films, not just cartoons, but of people, right, are not filmed as you see them. It's cheaper to get the technical people to take a picture of Caroline and make her walk.
With a green screen behind.
I don't know, but the point is, if you were a film star who charged, it might be cheaper to make the software actually make you walk rather than having you all day walking around doing the things. You mean you would be an actor on the stage, but at times, especially, at times the software engineers create the moving pictures by making a series of small changes, morphing the picture so it looks as if the person or the whatever it is, the vehicle or whatever it is actually moving. But
or they replicate, like especially when there's crowds. Titanic was the first one where this was famously done. The scene in Titanic where the ship was sailing out of Southampton Harbour and everyone was waving, that was CGI. That wasn't real. And with all these battle scenes, Lord of the Rings, a lot of the aviation scenes these days and bombings, and it's all CGI. And they're doing, especially when there's a lot of crowds or a lot of airplanes in the sky, it's the same principle.
Yes, and it's so many pictures that you think you're seeing something continuous. What you're actually seeing is such a small change that you don't recognize the change. And what Escher is showing you here is actually you can see the change, but he's not putting all the many stages in between. But it's
originally the movies were called, the reason why they're called movies is because they are moving pictures. There are lots of stills. The very original ones were simply still pictures, literally drawn still. And the cartoons, originally the Disney cartoons, were all stills that are just filmed at a rate so that the human eye they look as though they're moving to the human eye.
So the mathematician studies this, or it's very mathematical programming, the CGI. That's really what I'm trying to say. And it's all to do with this continuous change. And also these ideas that we've been talking about reflection, rotation, and translation. Those groups of transformations are all built into the computer program that is used to make these films. I mean, there's a lot of mathematics in it. And here you can see, I'm not sure whether he thought of films and animation in films, but he was certainly thinking of an artwork to put on the wall to explore these ideas. She was thinking that. And we see them in other works that he's done. Now here you see this, which is called Sky and Water. And here you see the grey birds at the top, or blackish grey birds, right? And as you go down, they get darker and they then merge into the dark water at the bottom. And as if you start looking at the fish at the bottom, which is distinctly a fish, and go up looking at the fishes change and then they lose their shape, and at the top they become the sky. And there you have the metamorphosis of the fish into the sky and the birds into the water.
Those are clearly geese. I'm very happy to actually see a bird I recognize. Those are geese. The top one is anyway. But the thing, it's nice because he's chosen both geese. Well, I don't know, fish don't do it quite so much, but geese do fly in that triangular formation. So it's really nice that he's used geese because that is a very natural form for them.
There's metamorphosis again. Now the next one, there's this whole idea of Mobius bands. We use this with children just to begin to get them to think a bit about an area of mathematics that's called topology, but this is just baby stuff, really, to take the Mobius band. But what Escher has done with this Mobius band he's actually merged it in the middle, where he's done this tessellation of horsemen, the grey horseman and the orange-red horseman fitting together. And he's actually, again, he's exploring the flat 2 dimensions and the coming out into 3 dimensions. So in the middle, he's flattened it, and then, although it's all 2-dimensional, of course, but he's very cleverly suggested the 3 dimensions, because you need 3 dimensions for the Mobius band. It's amazing, that I love it. And here you've got some more Mobius bands. Okay, the one on the right with the insects on it, that one has just got 1 twist. So what you do to make a Mobius band is you take a strip of paper and you do 1 twist and then glue the piece together, so you make a continuous path.
That's what, and it's a nice thing to experiment with. If you loop together a loop and just make a cylinder, basically 1 loop, then you can draw on the inside, and you've got 1 line that
one surface.
Here, 1 surface. But yes, but if you draw, you've got 1 line that joins back together with itself. And you draw on the outside, you've got another line that draws back together on itself. And so you've got 2 lines, 2 surfaces, 2 lines. Then you twist 1 twist. Do the same again.
That's a Mobius band.
Start here and start drawing right down the center and see what happens. So glue that together to make it easy for yourself, and do that and see what happens.
Now, if you look at the insects, right, you'll see that some of them are inside the band. As they go round, the inside becomes the outside, and then they're on the outside, and then they get into the inside again. And as Caroline just explained to you, if you imagine drawing a line.
I didn't explain the second part, though. I let
well, they can do that themselves.
Find out for themselves. Is that an optical illusion, or can we actually do that in real life? Can we make 1 path for the ants in real life?
So Mobius strip 1 on the left, right, has got 2 twists in it before you glue it together again.
So that's another nice one to experiment with. So we started off with no twists, and then I said do 1 twist now and draw the line, or cut it in half. That's another really interesting thing. Do this with. Now I'm going to give it an additional twist, which is what the one in the middle is. It doesn't quite look like that because it's made out of paper, but this has got 2 twists in it. Then what's going to happen? How many surfaces have we got this time?
Okay, so he was looking at and making his sort of artistic representation of these Mobius strips. Fascinating.
Thank you so much, everybody. See you next week.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest